All right, ladies and gentlemen, so I was cut off in the middle of that one, so we're starting with another one here. We were in the middle of this problem 3a, trying to figure out the mole fraction. So we had determined that the moles of my CO would be 0.55. Then we were figuring out this total moles of the mixture. So I had 0.2 moles for my H2, 0.3 moles for my CO2, 0.55 moles for my H2O, and 0.55 moles for my CO. Would give me a total of 1.6 here. So if I put that 0.55 over my total moles in the mixture of 1.6, and remember that's how we calculate mole fraction, this would give me an answer of 0.34 here. So that should be my final answer. Now in the next question, they want me to use those concentrations to calculate the value of K. Remember, my K is going to be the concentration of my products over the concentration of my reactants, all raised to their powers of their stoichiometric coefficients. So I'll have the concentration of H2O times the concentration of CO over the concentration of H2 times the concentration of CO2. And again, they give me those equilibrium concentrations here. So I'm just going to plug them in. I've got 0.55 for both my CO and my H2O. Then my H2 was 0.2 and my CO2 was 0.3, all raised to the first power because all stoichiometric coefficients of 1, should give me an answer of 5.0 here. Again, K values are unitless. Then same thing as before with question C. This is from an older AP exam. We do not need to know how to calculate between KP and KC here. Okay, so in question D, they're telling me that I lowered my amount of my CO by 30%. So 30% of the CO is converted back to CO2. So I know that at equilibrium, I had 0.55 molar of my CO. If 30% of that is being converted to something else, well, I need to know what that 30% is. So I'm going to take that 0.55 times 0.3, which will give me 30% here. That gives me 0.165 molar change. That means that my CO is going to decrease by 0.165 molar. Basically, what this is telling me is that my reaction is shifting in this direction here, telling me that I'm going to decrease my CO and my H2O, and my CO2 and my H2 are going to increase. The amount that my H2O and CO decrease by will be the same as the amount that my H2 and CO2 increase by, because everything's in a 1-to-1 stoichiometric ratio here. So if I know that my CO is lowering by 0.165, well, I can still set up my K in the exact same way, but now my concentrations are just going to be a little bit altered. So for the concentration of CO, it's going to be 0.55 minus 0.165, which will give me 0.385. And it'll be the same thing for my H2O. That's still being lowered by 0.165, still was starting at 0.55, so that's 0.385. Then for my reactants, remember we were shifting reverse here. We were using up more of our products to make more of our reactants here. They're going to increase by the same 0.165 because they're all in a 1-to-1 stoichiometric ratio. So if H2 started at a 0.2 plus that 0.165 would give me 0.365 here. And my CO2 started at a 0.3, increased by 0.165, should give me 0.465 here. Plug all of this into my calculator, and I should get about 0.87. Okay, now this one here. Now this one's telling me that in a different experiment, we're starting with 0.5 moles of H2 and 0.5 moles of CO2 in a 3-liter reaction vessel. They're asking me to calculate the equilibrium concentrations in moles per liter, which is the same thing as molarity, for CO in this reaction. So I'm going to rewrite my reaction, and I know that it's H2 plus CO2, and that's, in equilibrium with H2O and CO. I need to know my initial molarities here. Remember, molarities is moles per liter. I'm given the moles of each of my reactants and the liters of the container. So to calculate my molarity, I take 0.5 divided by 3 for each of those. So each of these will start at 0.167 molar. My products will start at 0. Again, that's my initial. The changes, my reactants will decrease by this factor of X. My products will increase by this factor of X. So for H2 at equilibrium, 0.167 minus X. For CO2, again, 0.167 minus X. H2O will be X, and CO will be X. I cannot assume that anything's negligible here because my KSP is not written with a negative exponent here, right? Sorry, not my KSP. My K value is not written with a negative exponent. My K value is written as 5. Yeah, that's a very large number here. So when I'm looking at this equation, I'm going to set up my K. I know that my K is equal to 5, and this is going to be equal to X times X over 0.167 minus X times 0.167 minus X. Now I could solve this using the quadratic formula, but I actually see something a little bit easier here. Both the numerator and the denominator in this fraction are squared. So I can easily just take the square root of both sides of this equation, square root of 5 and the square root of this right here. Square root of 5 is something along the lines of 2.24. Then if I take the square root of the squares of each of these, well, the square root of X times X is X. And the square root of this 0.167 minus X times 0.167 minus X is 0.167 minus X. And now it's some simple algebra to solve for my X. Again, you could use the quadratic formula, but you should end up with the same answer of this X, this change, being equal to 0.116. They're asking me for the concentration of CO at equilibrium, which is equal to X. That's what we saw in this rice table up here. So this concentration will be 0.116 molar. Okay, moving on to our last question here. First one wants me to write the equilibrium constant expression. That means the K value. This one's specifically going to be a KSP because I'm talking about the solubility product, but you could have just written this as K here. And this KSP is always equal to the concentration of my ions dissolved in solution raised to the power of their stoichiometric coefficient. Solids are not included here. So I should have had K equals the concentration of Pb2 plus times the concentration of I minus squared. Now they want me to calculate the molar concentration of I minus here, and they give me a big key piece of information right up here in the passage. They tell me that at equilibrium, Pb plus 2 is found to be 1.3 times 10 to the minus 3 molar. So when I'm writing out my rice table here, again, we start with PbI2. It's in equilibrium with those Pb2 plus ions and the I minus ions. I know I'm not including my solid, but I know that these are both starting at 0. My Pb plus 2 will increase by X, and my I minus will increase by 2X because of its stoichiometric coefficient. And I know that this Pb plus 2 is 1.3 times 10 to the minus 3 molar at equilibrium. So 0 plus X is equal to 1.3 times 10 to the minus 3. That tells me that X is equal to 1.3 times 10 to the minus 3. So I minus then is 0 plus 2 times that X, which would give me 2.6 times 10 to the minus 3, and that's going to be in molar here. Then if I want to calculate the value of that KSP, that K, I'm using that same equation from above, from part 1. I'm plugging in the value that I just solved for here. So I know that my concentration at equilibrium for Pb2 plus was 1.3 times 10 to the minus 3 from the reading. We just solved for I minus. It was 2.6 times 10 to the minus 3. This one gets squared because of this stoichiometric coefficient of 2. I plug that into my calculator, and I should get 8.8 times 10 to the minus 9. Again, K is unitless, so this is my answer here. Okay, then moving on here, they're asking me what the difference would be if I made this in a 2-liter solution. Okay, instead of the original solution that I was given at the top, instead of that 1-liter solution. What we need to think about here is that the KSP is not affected by the volume. That K value is really only changed by a change in temperature. Nothing else is affecting that K value. It should be a constant. That's why we call it an equilibrium constant. So if that K value is staying constant, then my concentration should be staying constant. I'm not doing anything that would shift the equilibrium here and change these concentrations. So that K value is not dependent on volume. So the concentration of my Pb2 plus would still be 1.3 times 10 to the minus 3 molar. And the concentration of my I minus would still be 2.6 times 10 to the minus 3 molar. Again, that K value is really only affected by temperature. If we're not changing the temperature, we're not affecting that K value, and we're not shifting the equilibrium in any way here. But if we look at question C, now we're talking about adding the solid NaI to my solution that still has my PbI2. And what I should immediately notice is I have this common ion of I minus. So NaI is fully soluble in water. We know that group 1 metals are always completely soluble. So this will fully dissociate into ions, and I'll release these I minus ions. Again, if I take a look at the reaction that's happening here with my PbI2, I'm dissociating this PbI2 into Pb2 plus and 2I minus here. So if I add this NaI, and NaI is giving up these I minus ions, or making these I minus ions, that's really like saying I'm increasing this concentration of I minus. And that's going to throw my equilibrium out of whack. So we have to look at Le Chatelier's principle here. If I'm increasing this I minus by adding the common ion of I minus, well, Le Chatelier's principle tells us that we'll shift away from that increase. We need to use up all these extra I minus ions. So these ions are going to come out of solution and make the solid here. Whenever we're looking at talking about the solubility, we're talking about that solid turning into ions. If something has a higher solubility, it will have more ions than solid. If it has a low solubility, well, it's going to exist more in the solid state and not really dissolve at all. So it wants to know what happens to this concentration of Pb plus 2. Well, if I'm shifting to favor the reverse reaction here and making more of the solid, that's going to happen at the expense of this Pb plus 2. It's going to be used up. So it will decrease because of this common ion effect causing the shift in equilibrium. Okay, so looking at this one, this was the last thing that we did in class yesterday. Okay, so we're looking at that Q value compared to the KSP value in a double replacement reaction. So in this double replacement reaction, we're reacting together BaNO32 and Na2CrO4. And they tell us that this salt might be made here, this BaCrO4. Well, this BaCrO4 has to come from the barium ion here and the CrO4 2 minus ion right here. So the first question is asking me to calculate the molar concentrations of Ba2 plus and CrO4 2 minus, assuming that the volumes are additive, meaning that we're adding the volumes together to determine these molarities. So I have to figure out the moles of each ion first. So for my Ba plus 2, I know I'm starting with 500 milliliters, which is 0.5 liters. And if I multiply that by the molarity, which is 8.2 times 10 to the minus 6 moles per liter here, that cancels out my liters, and I'll be left with moles. And when I do that, I should get 4.1 times 10 to the minus 6 moles. And again, that was for Ba2 plus. I need to get back to the molar concentration, which means molarity or moles per liter. So I'm going to divide this by the new volume. The new volume is found by adding together these two individual volumes. So if I mix together 500 milliliters and 500 milliliters, I make 1,000 milliliters, which is 1 liter, which they give me right here. So this number of moles divided by 1 liter would give me 4.1 times 10 to the minus 6 molar Ba2 plus ions. And that would be my molar concentration for Ba2 plus. And it's going to look absolutely identical for my CrO4 2 minus here because I have the same numbers. So still 0.5 liters, still 8.2 times 10 to the minus 6 moles in 1 liter. They have to give me 4.1 times 10 to the minus 6 moles of CrO4 2 minus. Again, over that total volume of 1 liter gives me that 4.1 times 10 to the minus 6 molar of CrO4 2 minus. Just so happened to work out that they were the same numbers in this problem. They're not always going to be the same numbers. Now I need to figure out if a precipitate forms. And if I'm figuring out if this precipitate is forming, I'm looking at my Q. And I'm comparing my Q to my KSP value. And this will tell me if this will happen. So if we're looking at KSP for this BaCrO4, remember we always start with the solid when we're looking at KSP in equilibrium with its aqueous ion. So with the Ba2 plus and the CrO4 2 minus that we were just looking at. We know solids don't get included in this expression, so my KSP would be concentration of Ba2 plus times concentration of CrO4 2 minus. Q is going to be set up the same exact way. It's going to be the concentration of Ba2 plus times the concentration of CrO4 2 minus. And I have those concentrations that I just figured out in part 1 here. So my Q is going to be equal to 4.1 times 10 to the minus 6 times 4.1 times 10 to the minus 6. And when I plug this into my calculator, I find that Q is going to be equal to 1.68 times 10 to the negative 11. If I compare that to my KSP, which I'm given given right here. Okay, his KSP is 1.2 times 10 to the minus 10. Well, this 1.68 times 10 to the minus 11 Q is smaller, so Q is less than my KSP. A precipitate can only form if Q is greater than KSP, so no precipitate will form here.